Now we come to the final operator of our system, which is the triple bar or double arrow as we're using. And triple bar sentences represent biconditionals. What I mean by a biconditional, it's a combination of two conditional statements, and one goes in each direction. So you might be thinking, oh, conditional statements were a pain. Now we're going to have these double conditionals. This is going to be even worse. Actually, no. Biconditionals turn out to be easier to deal with than regular conditional statements. So let me start off with an example of what I'm talking about. Suppose we have a statement like, you pass the class if and only if you ace the test. We actually have the tools to represent this kind of statement already within our system. Because if you think about breaking this statement down, it means you pass the class if you ace the test. That's the if part. And then we have and, which we can represent with the dot. You pass the class only if you ace the test. So now both of these are conditional statements. They can be represented with the arrow or horseshoe. And test yourself on how well you're doing with those. How should we represent the first statement? You pass the class if you ace the test. Well, recall that if you ace the test, the if signifies the antecedent. So the A part should be on the left in this conditional. That is, it should be A, horseshoe, P. We can also symbolize the second statement, you pass the class only if you ace the test. Remember that only if signifies the consequent. So that part that you ace the test should be on the right in this statement. We should have P, arrow, A. So we have these two conditionals with and between them. We can use the dot to represent and we can represent the statement, you pass the class if and only if you ace the test, like this. This type of statement is sort of common enough, and for various reasons is something that we want a shorter notation for. So that is why we introduced the double arrow or the triple bar. And what we're going to do here is we're going to introduce the double arrow as just an abbreviation for what we have here in front of us. So if we set up all the possible assignments of truth values for P and A, recall here that P and A are actual simple sentences of the language, so they will be assigned either true or false. So now, instead of dealing with just abstract inputs of metalinguistic variables, we're actually talking about potential assignments of values to the simple sentences of our language. But either way, we have the usual four possible assignments, both true, first one true, second one false, first one false, second one true, and both false. The main operator of this sentence is dot, as you recall. So we're going to use the rule for determining the truth value of a dot sentence to get the truth value of this sentence on every assignment. It has to do with the value of the sentence on its left and the sentence on its right. So in order to find the truth value of the dot sentence, we have to first find the truth value of both of these arrow sentences. Once we get the value of the dot sentence on every assignment, then we're just going to define the double arrow sentence so that its value is whatever the dot sentence turns out to be. Let's start with the first assignment. And we have to compute the truth value of the sentence on the left and right of the dot. So the sentence on the left is P, arrow, A. When both statements are true, the value of that is true. The sentence on the right is A, arrow, P. When both sentences are true, that's also true. So now on our first assignment, the dot sentence is true on the left, true on the right. Both sides true, so it's true. Now look at the next assignment. When P is true and A is false, P, arrow, A, if P then A, is false. That's the only time it's false, right? When the left side's true and the right side's false. Meanwhile, A, arrow, P, the left side is A, which is false, and the right side is P, which is true. Under those conditions, the arrow statement is true. So we get a false on the left and a true on the right. Our dot statement is false. Next, we have the assignment where P is false and A is true. So in this sentence, A, arrow, P, the left side is false and the right side is true. That makes the arrow statement true. Remember, it's only false when it's the other way around. And since on the other side of the dot we have A, arrow, P, and the left side is A, which is true, the right side is P, which is false, that makes that one false. So the dot statement on this assignment is false. And the last assignment where both are false, P, arrow, A, is true. Remember, it's only false when the left side is true and the right side is false. So when both sides are false, it's true. And the same thing happens on the other side of the dot. So we have a true on the left, a true on the right. So the rule for dot tells us that the dot statement is true on this assignment. Now, before we go any further, I want to point out to you a quicker way to do what we just did. I went through each assignment and computed the truth value of the whole sentence, the dot sentence, on each assignment. But it works out to be quicker and probably easier too if I go column-wise and compute the value of just one sub-sentence on all assignments. So I take the left side of the dot, the P, arrow, A, and I'm going to just write down the truth value for that on each assignment. And the only time it's false is when the left side is true and the right side is false. So that happens on the second row here, the second assignment, and then the rest are all true. And then I do the same thing for A, arrow, P. I know that the only time that's going to be false is when the left side is true and the right side's false, and the other values are going to be true. And now I can compute the truth value for the main operator on each assignment, and the rule here is dot, only true when both sides are true. So this one's true, false because the left side's false, false because the right side's false, and then finally true again. So now I have my values for the sentence P arrow A dot A arrow P. I'm going to just define the double arrow as having those same values on each assignment, on each corresponding assignment. So the double arrow ends up getting defined as something that is true when the sides are the same. Notice it's true when both inputs are true, the double arrow is true. And then also, when both inputs are false, the double arrow is true. But when they're different on these two middle assignments, then the double arrow statement is false. Now, for this example, I decided to use actual sentences of the language instead of metalinguistic variables. But when we define the value of the double arrow operator, we would actually use metalinguistic variables, and you'll see in the book that the definition uses variables. So you can see why I said that the double arrow or the biconditional is easier to deal with than the single arrow or conditional statement. The order doesn't matter. All you have to worry about is whether the sides are the same or not. Also, we don't have umpteen different ways in English of putting a biconditional statement. It can be stated with the if and only if clause, like you pass the class if and only if you ace the test. And there might be a few other ways. Just one that comes to mind, if I say you pass just in case you ace the test, then that seems like it's saying that you do pass in that case, but also just in that case. And that's all we have to say about the biconditional. So now we've finally gone through our entire system and done an overview of how the system is to work. And to sum it up here, there are 5 types of statements in our system. The first is simple sentences, which we think of as representing a statement like Al is home, and we symbolize with just a simple capital letter. The semantic rule for simple sentences is that they are just directly assigned a value, either T or F, either true or false. And then we have negations, which represent for us statements like Al is not home, and we symbolize those with a tilde, in this case, a tilde in front of the simple sentence that Al is home. And the rule for negations is that they are assigned the opposite value of whatever the negation of. We have conjunctions, which represent statements like Al and Bob are there, or Al is there and Bob is there, which we symbolize with a dot. In this case, it's between two simple sentences. And the semantic rule for dot is that it's only true when both sides are true. We have disjunctions, which represent statements like Al or Bob is there, or Al is there or Bob is there. And we represent those with a wedge, in this case A wedge B. And the rule for the wedge is that it's true as long as at least one is true, at least one side is true. And then we have conditionals, which represents a statement like if Al's there, then Bob is, which we're representing with the arrow, or alternatively the horseshoe, A arrow B, or A horseshoe B. And the rule for the arrow sentence is it's only false when the left side is true and the right side is false. And remember, that's the tricky one. Finally, we have biconditionals, which represent statements like Al's there if and only if Bob is. And we're representing those with the double arrow or triple bar, so A, double arrow B. And the semantic rule for biconditionals is that it's true when the sides are the same and false when they're different. So this concludes our overview of the system of propositional logic that we're going to be working with. And I hope you're going to find, as I do, that once you have an understanding of how the whole system works, the various applications about logical relationships that we're going to be exploring just sort of fall right into place based on how the system is built up. So we're going to turn to that next.